stopping that. Going to now we're going to go add, so having added this count of the times people infected, we're going to go provide a way of displaying it, of looking at this relationship, particularly between infection on the one hand and count of times infected. We know, generally speaking, the lower the income, the more times they're infected. But we're going to probe that more and check what it looks like. So here we go. So in order to display that, this is going to be information that we're going to show at a global level. And we're going to do so with a scatter plot. I'm doing this. We could do a histogram of the number of times you've had an effect, and all that's good, but we've seen those before. So I want to add in something new, and you'll see that it's actually a very useful lens. I think it's an incredibly powerful lens for understanding dynamics, the associations that emerge from agent-based models, and how those associations often change profoundly when we undertake interventions or examine other counterfactuals. So let's go see this. We're going to go to main, and we're going to explore some new properties of the toolbox afforded to us here in AnyLogic. Okay, so we're going to go down here on the left-hand side to analysis. And we're going to add in something of great significance. We're going to use it here, but it's very versatile. It can be used in other cases. And it's one of the workhorses to keep track of data and export data. Mark my words. Export data in a programmatic and automated way. So we're going to add a data set. It's called a data set. And a data set, job in life, is going to keep track of pairs of values. Most commonly, if it's in the model body itself, it'll keep track of pairs, one of which is time, and the other which is some value you want to keep track of. Like here, we could keep track of the cumulative number that have been infected by this point in the model, were we to want to do so. We could add that and keep track of it. But more generally, you can keep track of other pairs. And in this case, we're going to keep track of pairs of income on the one hand for a person versus their infection count thus far. And we'll see how that evolves over time. So this data set that we've added for the model as a whole, because different people will be contributing data in it, but this is going to summarize it for the model as a whole, and there'll be a scatter plot based on that. Now, this data set will be called income versus, I'm not going to put it first, I'm going to put it last. Income versus infection count data set. The reason I put it last is because I want the attention to be on the domain thinking, like income versus infection count, not on like data set. So I put the data set after to clearly label what sort of thing it is. When we autocomplete, et cetera, I know, oh, no, that's not what I'm interested in. But so I know it's a data set, but it doesn't distract from the domain significance that I'm keeping track of, in this case, pairs of income versus infection count. Okay, now it's important. This is a data set, and I said it can have pairs, and most commonly those pairs that's in the model have pairs of time and the value of some quantity, like the cumulative number of infections or number of people in the population or number of people with heart disease right now or whatever. If if a data set is in an experiment, then it normally keeps track of pairs, not with time, because the experiment runs the model as a whole. Boom, done. But the number of iterations, if it's running the model again and again, how many times it's run the model. That we'll be coming to that on another day, but not today. Okay, so we're going to use here, we're not going to use time as the horizontal axis value. We're going to use instead income will be the horizontal axis and count of times infected. But we're not going to fill it in right now. It's not like we have a certain value that we can put in there right now. We're going to keep a number of samples given by the size of the population. So initial, oh, I don't think you can. You have to specify a certain number. Well, that's not good. So we'll hold up to 10,000 samples. We'll only use a fraction of them. We don't want to kicking them out, evicting them. Now, this is currently down here among the things involving the model logic core. But morally, it should be further up because it's really a reporting thing. It has to do with epiphenomenal reporting from this model. So I'm going to put it reporting epiphenomenal quantities. Now, I would remind people who have come in recently that I posted crowding disparities version 3, and we are working now, bending our backs to the task of keeping track of, in a visual fashion, a scatter plot that shows income on the x-axis, infection count on the y-axis, where each dot is a certain person. So it's showing the association across the population between income and infection count, with the observation being that we have good reason to believe, based on the qualitative look at the network, that people in lower incomes have higher infection counts, and people in the very high incomes, very low infection counts. And we want to see the shape of that curve. And so version 3 has the recording of the number of times a given person has been infected. And what we've just done for those arriving is add in a data set, said we're not going to use time as a horizontal axis value. We uncheck this. And I set it to keep 10,000 latest samples. And we don't need to log it to the database. I don't know why this is. Yeah. Okay.
So
yeah,
default is on, but then model execution logging is off. If you point at
exactly.
that little light bulb,
yeah,
it'll tell you that it's not logging because execution logging is off,
right,
globally.
Okay. Yeah. Thank you, Wade. That's great. So if you want to debug the model or really study its behavior in detail, you could log there to the database. Okay. So we added this data set, which is going to hold pairs of values for a given person, for each person in the population. At a given time, each of snapshots, for each person in the population, there's going to be a data item here, a pair. The first element of the pair will be their income. The second element of the pair will be the count of times they've been infected thus far, the cumulative times they've been infected thus far. And we're going to add in a plot. Okay. Now, really, that's a scatter plot. Properly speaking, it should be called a scatter plot. And I think calling it a plot is It's the most unfortunately blunt term. It's a plot. It's from the analysis palette, like as was the data set before it. Okay, so this is going to be called scatter plot, income versus count infections. And oh my gosh, I don't know why I'm being so inconsistent. It should be scatter plot should be the end. The type of thing I like to put in the end. You can choose your own convention, but that is my defined convention. Income versus count infections scatter plot. There we go. That's what its name is going to be. And its data set is going to be this data set we just set up. So this is going to be income. So its title is going to be income horizontal, so the x-axis, versus infection count. It's the y-axis or vertical axis. And the data set is going to be income versus infection count data set. Now you can see why I'm careful about naming them. Because if I just lived out whether it's a data set or scatter plot, I wouldn't have known which to pick. Well, I would have had to look after it to see. I want the one that's a data set. This is the one that's a data set. So it wouldn't have been that bad, but okay. So this is, oh, it didn't even fill it out. Income versus infection count data set. There we go. Okay. 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 Now, thank you, Joe. Now we need, you may remember, there's this idea of observer processes periodically reporting things from the model. Beyond the processes that are governing the behavior of the model, governing the endogenous processes, there's these epiphenomenal ones, these ones that don't change model evolution, but observe it. They're kind of above it, and they're looking down and reporting these things. And they're driven by processes too. And what we used in our model yesterday to report in this way, the histogram, was a little event. And general events are workhorses for this, for these observer processes. They fire off at a certain time and let us do what we want to do, which is report periodically on the status of the model. So what I'm going to put here is a event, and I'm putting it near this scatter plot. Oops. Oh, you'll notice I moved it up because really these things are epiphenomenal. They have to do with reporting processes. I like to cluster them together because they kind of go together. Birds of a feather flock together. Okay. So this is an event, and I'm going to call it, hey, come on. Okay. I'm going to call this populate income versus infection count scatter plot event. And I'm going to set this to go off cyclically every one, not millisecond. Don't do that. You got to be really careful with this. If you set it to millisecond, your model will ground to a halt and you'll be miserable and you might not know why it's taking so long. And you could consult with Wade and he'll help diagnose that there's a silly plot that's updating every millisecond. You don't want to do that. Others have been down that road, and it's particular danger if you forget to set the time unit of your model and you leave it as seconds, and then you build some things to your model, and then you realize, oh, I got to go change it, and you change it, but you don't realize those things that you built are using the default time unit, which it was seconds, and they're still seconds. And so you've got your model's plots updating every second when your focus is on the year scale, which is crazy. You don't want that. Been there, done that. That way lies madness. Quaid, an old horse like me has seen that many times. I had a call from a prominent infectious disease modeler in Canada asking me to help. Yeah. Anyway. Okay. So what are we going to do? What's the heart of this? We need this event to go off every month and do something. That's the job of an event, and undertake some action. What is the action it will undertake? It will populate that data set that is plotted by this plot. You remember this is very similar to the histogram yesterday, right? We have a data set of sorts. There was a histogram data object. Then we have a plot that depends on it, and then we need an event which populates it. Okay. So this thing is becoming very slow, and I'm not sure if it's Zoom dysfunction or what, but okay. So what we want to do is first we want to reset the data set just like we did yesterday. That was the first step. The data set, we want to reset it, clear it out, tabula rasa, clear out all the data points that were accumulated thus far. Next, we want to populate it. Okay, now I taught you a way yesterday to loop through the population. And we could do that same thing. I'll show you what it would look like. And if you're a happy camper with that, you're welcome to stick with that. But I'm going to show you a slicker way yet that enjoys as many advantages, many virtues. So for what am I doing? What am I doing? Sorry. When you know too many languages, you fall into habits. For each person in the population, okay. For each person in population, person P in the population, sorry, I'm thrashing. For each person P in the population, you're going to do you're going to do the name of this data set dot add the two things that you want to record for that person. What are the two things you're going to record for that person? Can anyone tell me? What are the two things that would be put into the income versus infection count data set from each person? Anyone? Their X and their Y. The first begins with I, and there's an N after it, and there's a C, and there's an OME. I'll give you a hint. The first thing you add for that person is their income. What's the other thing we want to add? What could that possibly be? Yeah, their infection count. Okay, so how do we get a person's income? Well, if we have a person called person, we're going through each person in the population, we call them person, lowercase p. So we ask for their income, and then there's a thing called monthly income. So we're going to go through and ask for their monthly income. Okay, here we go. So we're back here. We're going to ask for their monthly income. And we're going to ask for their count of infections thus far. Okay, this is exhibiting slowness. Count times infected. And then we end our parentheses and then we do a semicolon. We need a semicolon because we're saying, do it, make this happen, change this. It's a command, like update this by adding them into that data set. That data set, you may recall, is designed to take pairs of values. And so we're populating here, having cleared it, taking pairs of values and adding it into it. And then it will display it. So that's a perfectly good way. And if you are comfortable with that, I'd say power to you. You can leave it like that if you want. I'll show you the other way, which is sweet in one line, and it goes like this. Population dot for each person in the population, called P, we will add that person's income and data set to this. And that's it. And so I'll put that, if you want to see it, you don't have to do both. No, you only do one or the other. If you like this, do it. If you prefer this other thing, because it's one line and just says, hey, for each person in the data set, add their income and ton of times infected to the income and count data set, then that's pretty short and sweet. And it's doing it for each person in the data set. And it doesn't have to have these ungainly curly brackets. So I'll put in a comment. It says, like, an alternative to the line above would be to do the following, in case you want to understand that. An equivalent alternative to the line above would be to do the following. Okay. So we populated the data set periodically every month. And this scatter plot is designed to be updated based on designed to plot that out. Okay. So we're going to go run this, run early, run often. And we'll want to keep track of, in our expectations, of the time here, because we're going forward a few days at a time. We're about a week in. People have gotten infected. It's at a very high level of infection. Oh my gosh, we forgot to set the settings. It's looking quite horrendous already. So we forgot to set the preferences for the data set, and it looks like a nightmare. Okay, so here we're going to go back to this data set, or sorry, to the plot, and we're going to go down to the appearance area. And we don't want to draw the line. Okay. We want to uncheck draw line. Okay. Great. So having done that, let's run it again. Let's let it go forward. Its very first update is going to be for the time 0. So it actually will have something there from the get-go. Here we go. So even as we're going through the first few weeks, this is the initial state. There's some people predominantly of low income that are infected once. Most people are infected 0 times. Now we're getting week, month 2. Some people, predominantly low income, have been infected twice. A larger number of people have been infected once. And then there are a large number, particularly very wealthy individuals, who haven't been infected at all. Let's keep on trucking. Here we go. Some people have been infected 3 times, and we'll keep on going here. I want to check how often this updates. I set it to update every day, and it really doesn't need to update every day. And that's probably going to impose some performance costs. So I'm going to stop this. And maybe I'm wrong. Wade, maybe you could tell me, if I set it to not update at all, my observation is it's pretty robust for updating if you have it linked to a data set directly. But I'm interested in your insights to that.
Yeah, I can confirm that you can say do not update on the plot, and it will still update provided the data set is being updated.
It has been updated. Yeah. Okay. Right. Great. Okay. So we're running this again, and hopefully we've secured some economies. From that, it seems to be running a bit faster. I'm going to run it at full tilt. Here we go. Okay, we're seeing an interesting pattern come out. It's a distinctly nonlinear pattern. There seems to be a kind of a drop off here. Maybe it's a bit less steep decline, but then we have this very long tail here. So I'm going to truncate it. It's okay with you here. We know people beyond a certain point, nobody's getting infected beyond, like, from appearances, maybe 2,000 or something like that, 1,500. So I'm going to say 2,000. So forgive me. I'm going to go post this in just a second if anyone wants that, but I'm going to go to this scatter plot, and I'm going to go down to the scale area. Here we go. And I'm going to set there to be a fixed horizontal scale going between 0 and 2,000. Okay, so that's an income between $0 and $2,000 per month. I will say that I wouldn't take I honestly, I should have called it weekly income, to be honest, but I made my mistake. Okay, so I'm going to post this model in case you're having any trouble and you prefer to use the one I'm using. It is over there. But I want to use this as an opportunity to reflect on what we're going to see, because it's quite interesting, actually. And it furthers some points that, I've been trying to make about the relationship between dynamic models and indeed complex systems, coupled nonlinear dynamical systems, evolving systems, underlying systems on the one hand, and the data we see coming out of them. So I'm going to zoom in a bit here. And I'm going to speed this up a wee bit, maybe not full tilt, but I'm going to. So here, a couple months are passing. What we're seeing is some sort of ambient relationship emerging. There are some, anomalies or outliers here. But by and large, the higher the income, there's sort of this gradient down here. And remember, above here, certain point, there's no. Yes, thank you, Jeff. So I'm not running it at full tilt. I want to emphasize the emergence of this pattern as the model, the endemic situation, the model is evolving. You notice Jeff, some of his people have been infected 60 times, 70 times, 80 times. We're still down here at a smaller number as I'm electing to run it more slowly. But you see this pattern emerging. And don't forget that above a certain level, it's all zero. I'm going to speed this up a little bit, but I think you see the general character. Why are people moving up over time? Can anyone say? Like, why are these individual dots moving upwards? Anyone? Well, because people are getting infected more. Each dot is a person of a certain income. That ain't changing. But they're getting infected more and more times, except these folks, these rich folks. They're not getting infected at all. But we're seeing the emergence of a pronounced disparity. And as time goes on, folks are moving up. These folks were closer to even with these, but now they've been moving up. You can't maybe see it at this rate, but they've been moving up faster, and it's getting sort of this extending down. You could see it here that there's this long tail in this kind of intermediate income segment where you have a material decrease in the count of times infected once you reach a certain point. I'm going to pause that. I'm using a little button down here that's kind of cloaked, but you'll notice sort of up at this area. Well, it's worth reflecting on. This is an association, right? It's an association between income and infection count. Is this because in the model, I have people with higher incomes, exempted from being sent infections? No, they're not explicitly exempted, but it's an emergent feature of the connectivity of the network combined with how infection, exposures are transmitted over to neighbors in the network. That induces a higher burden and lower income because and the network is connected locally with a certain distance, and people in lower incomes are living in more crowded conditions, and so they tend to be infected more. And the overall effect of this and the duration of immunity and that exposes and one after waning to being infected again, that induces an emergent pattern with respect to this. And you'll notice that I won't say it's flat, but it's not so steep here. And then it starts to decline fairly strongly, from, let's say, 700, where it's somewhere up here at 400, to twice that income at 1,400. It's down at 150. So it's a difference of almost 3 times. There's this tail down here. A little bit of income in this lowest quartile, lowest segment, which may be most of the people in the model. I think it's most of the people. There's very little change. It takes a certain level of income, and by extension, a certain threshold of number of people to whom you're connected. Below that threshold, the number of people you're connected, then then you start to see an impact of income. So this is a non-linear association. Like you wouldn't want to examine this directly, assuming some linear covariation between income on the one hand and infection count. This is induced by a bunch of features in the network. And I would posit that if we were to intervene, say, heavily on lower income, or if we were to put in place vaccination or screening campaigns to more quickly locate infected people, or engage in social distancing, or lower the crowding level by giving people access to better resources for affordable housing that are less crowded, then you would have a material decrease in infection, and that might change this pattern. So I'd like to now examine that. So specifically, I'd like to take a look at some basic intervention, kind of motivated by what we did earlier. These are very stylized interventions, but they're going to get at the role that different characteristic parameters play. So to that end, focusing on scenarios, rightly, we should call this existing simulation, which uses all the default values. You don't see any bold thing here. Baseline. And I'm going to stop the recording here.